Hi and welcome everyone. In this lesson we will talk about the overcurrent protection guide for PV systems. We will learn in this lesson how can we select circuit breakers or fuses in addition to the cables inside a PV system. So let's start. If we look at a PV system here like this one is a big PV system consisting of a group of strings. These strings will form sub-arrays. So if you look at here, you can see one string, as you can see here, this is one string with a positive and negative terminal, as you can see here. This is another one here with a positive and negative terminals, another one and another one. These strings are combined together using something which we call a string combiner box. What is the function of this component here? Its function is to combine all of the strings into two terminals, positive and negative. Now, as you can see in this figure, you can see this small rectangles here, red rectangle, black, red, black. What is this representing? This representing the protective fuse for protection of the string and cables. Okay. Now what will happen here if you have a very large PV system, very big PV system? So we have this group of strings forms an array, right? And this group of strings forms another array. Now when we have multiple arrays in one PV system, we call them sub-arrays. So we have this one, the first one here is called sub-array 1. Let's say, for example, this one, sub-array number 2. If we have another one, sub-array number 3, and so on. So when we take all of these, you can see here positive and negative, and we combine them using something which we call sub-array combiner box. What does this mean? It combines the sub-arrays, similar to this one here, which is called a string combiner box. It combines group of strings. So this one combines group of sub-arrays and forms final two terminals, give us the two terminals of the array. So as you can see, this array has also a protection device called array fuse link. Now the first question here, number 1, do we need fuses in the positive and negative terminals, or it is enough to add positive fuse on the positive or a breaker on the positive terminal? According to the Cooper Busman is a company for protective devices related to PV systems. They provide PV fuses. Okay. According to them, you need fuses in the positive terminal and negative terminal. Okay. However, most likely or most of the PV installation companies use fuses in the positive terminal only. Okay. Now, second question. Do we need to add fuses in every PV system? Do we need fuses or a protection device in every PV system? The answer is no. You don't need fuses all the time. We will learn when we need exactly in the next slide. So as you look here at this system, you can see that we have here number 1, which is fuses. You can see here photovoltaic fuse links or PV fuses, and this one is a fuse holder that holds this fuse. And we have another type which we will see in another lesson called the inline fuse holder. This one, as you remember, the two terminals of the PV panels are MC4 connection, right? MC4 terminals. This MC4 can have something which is called inline fuse holder. We can add to them inside them a fuse. Okay, And we have also inside the combiner box a surge protective device, which is used to protect against lightning arrestors, or lightning, not lightning arrestors, lightning surges. And if you look at the rest of the system, we have also fuses or circuit breakers. So let's start by questioning ourselves. Do we need overcurrent protection for each PV string all the time? Actually, no. When do we need protection or overcurrent protection? So first, if you have one single series string, just one string, okay, if you have a PV system like this one here, just one string going to a charge controller, okay, one string here with a positive and negative terminal going to the charge controller. If you have one single string, according to article 690.9 in the NEC code, NEC or the National Electrical Code, you don't need any fuse. Okay, you don't need any fuse, so you don't need to add a protection for this type for one single series string. Okay, however, there is some conditions. The first condition is that this string should not be connected in parallel with other sources. So there is no external sources connected, such as a parallel connected source circuits, batteries, or any backfeed from inverters. In this case, you don't need a fusing. Number two, this cable here, which is a two terminals going to the charge controller, must be sized at 1.56 multiplied by the short circuit current of the PV panel. So if you look at the PV panel here, this PV panel on the datasheet or the specs, it has a certain I short circuit. So when we size our cable, it must be 1.56 multiplied by I short circuit. This is the minimum value, okay? So let's understand why 1.56. So 1.56 is divided into two parts. It is 1.56, it is 1.25 multiplied by another 1.25. So what is the first one? Here, the panel, what is the worst current that can go out of the panel? Okay, what is the worst current? The worst current is I short circuit. Now you have to understand that the I short circuit on the panel is at condition of irradiance 1000 watt per meter square. Okay, now let's say, for example, in any time of the day, let's say at noon, for example, the 1000 watt per meter square goes to 1200 watt per meter square, for example. So as irradiance increase, the total current going out of the panel will also increase. So it means that the short circuit will also increase. So we have to account as a safety factor for the presence of over irradiance condition. So in this case, we add 1.25 as an over irradiance coefficient as a safety factor to accumulate for any increase in current due to the increase in the irradiance. Number two, second factor, 1.25. It's called the derating factor, or known as 3-hour NEC. So what does this even mean? So the NEC or National Electrical Code says that, or states that if you have, for example, a cable or a breaker or a fuse or any element or any electrical element in which current will go through it more than 3 hours continuously. So if, for example, if you look at the PV system here, of course the current will go through this cable more than 3 hours continuously. That's why you have to derate our cable by 80%. Okay, so for example, if we select a cable of 100 ampere and we know that current will go through it more than 3 hours continuously, we have to only load our cable by just 80 amperes. Loaded it by 80% only. Why? Because this current, when it goes through the cable, it will cause heat energy and increase the temperature of the cable. That's why we need to underload or decrease the loading on this cable. So if you have 100 amperes, you have to go down to 80 amperes only. So in order to choose a cable, we need to multiply by 1.25 in order to accumulate for derating by 80%. Okay, I know you don't understand, right? Okay, let's say for example that our current is 100 amperes. We need this cable to be loaded by 100 ampere at full load. Okay, so what I'm going to do is that I'm going to take the 100 ampere required and multiply it by 1.25. So we will choose a cable of 125 amperes. Okay, then when we apply the derating by the NEC code, 3-hour NEC, when we multiply this by 80% to load this cable by just 80%, we will get the 100 amperes required. So we oversize or choose a higher cable at which when we decrease its rating or derate it by 80%, we will get the required current that we need. Okay, I hope it's clear. So we have 1.25 multiplied by another 1.25, which will give us 1.56. So the rating factor again for the 3-hour NEC, when we have a current going through a breaker or a fuse or a cable for more than 3 hours. That's why we add this the rating factor of the NEC international NEC code. And 1.25 to accumulate for any over irradiance that will lead to increase in current. Okay. Now another thing that you will find these rules that I'm talking about in this slide similar in the IEC code. So in the IEC you will find it is similar to the NEC. Same rules. If you have a single string, you don't add any fuse. Okay. Now what if I have two strings in parallel? We have 1 and 2. Let's say we have two strings. Here positive and negative. We have two strings like this. Take this one here and this one here. This one here and this one here. Okay. Here positive, negative, positive and negative. Okay. So this is the first string and this one is the second. If we have two strings in parallel, you don't also need any fuse. So we don't need fuse in the single series string and we don't need any fuse in the two parallel strings. Okay, this is according to the NEC and IEC. So here it says that the fusing is not required if the short circuit from the current does not exceed the ampacity of the conductors or the maximum overcurrent protective device size specified on the PV module nameplate. Okay, so what does this even mean? So as you can see, we have two parallel strings. Now let's say, for example, that here, okay, our panels. Let's say, for example, a short circuit occurred here, short circuit. So what will happen here? This panel will not provide any current, right? However, this panel will start supplying electrical current that will go like this to the short circuit location. So what is the maximum current that will go from here to here? The maximum current will be 1.25, which is the over irradiance coefficient, multiplied by I short circuit. So this is the maximum current that can go from here to here. Okay, so as you remember that we said that we select this cable as 1.56 multiplied by I short circuit. So this cable can withstand this short circuit current. Okay, so the cable here can withstand 1.25 multiplied by I short circuit because it is 1.56 multiplied by I short circuit. Okay, this is the first condition. Second condition is that this panel On the specs, it has a maximum overcurrent protective device size on the specs of the panel. Let's say, for example, 15 ampere. So it means that the maximum fuse that I can add, or maximum current that the panel can withstand, is 15 amperes. If 1.25 multiply short circuit less than 15 amperes, then it is fine, you don't need any fuse. Okay, we will see this in the next slide. So as you can see, each string will give us a maximum current of 1.25 multiplied by I short circuit, and our cable is 1.56 or higher. So the combined circuit fault current is not large enough to cause any damage to cables or modules. That's why fusing will not be required, or we don't need any fusing in this case. Now let's understand what I'm talking about. So we have here the short circuit current that we use, and you can see here the maximum series fuse rating, which is 15 ampere. What does this represent? This representing this part. You can see here maximum overcurrent protective device specified on the PV module nameplate. So you can see 15 ampere. If we have two string parallel, if the current, which is 1.25, worst short circuit current, 1.25 multiplied by 8.87 will be, of course, less than 15 amperes. So you don't have to worry about anything, okay? Similar to here, another panel that we used in our design, I short circuit and series fuse rating 15 amperes. This is the maximum fuse that can be installed, okay? Now, when do we need overcurrent protection? Starting from 3 strings or more in parallel, according to the NEC, we need fusing, okay? Why? Because you will find that in this scenario, if you look at here, we have 1 string, 2, and 3, okay? So this one will give us maximum short circuit current of 1.25 multiplied by I short circuit. This one will give us a maximum current of 1.25 multiplied by I short circuit. So let's say, for example, we are talking about this cable or this panel has a fault inside a short circuit. So we will get a current coming from this string to here, and the current coming from the other string here. So what is the total short circuit current? It will be 1.25 multiplied by I short circuit plus 1.25 multiplied by I short circuit, which is 2.5 multiplied by I short circuit. And if you remember that our conductor here is sized as 1.56 multiplied by I short circuit. So as you can see that the short circuit current is higher than the ampacity or the capability of the cable, higher than the ampere that the cable can withstand. That's why we need a fuse to be added here to protect the cable against short circuit. Okay, that's why starting from 3 or more, we start needing a fuse to protect, or a breaker, as you would like. So you can see the combined current, as you can see here, is higher than the size, which is 1.56, as well as, of course, the series fuse rating of the PV modules. Under this fault condition, the conductor and the PV modules will be subjected to damage, because here, for example, let's say these two currents, let's say 16 amperes. Okay, and this one has a maximum fuse rating of 15 amperes. In this case, the modules will be damaged or be burned. That's why we need a fuse to protect both of the modules and the cables. Let's have a summary for what we just have said or explained in the previous slides. So if you have a string here, as you can see here, number 1, if a PV system has 3 or more strings connected in parallel, we need to have each string protected. We need a fuse for each string. Number 2, if the system has less than 3 strings, it will not generate enough fault current to damage the conductors or equipment or modules. Number 3, if we have 3 or more strings in parallel, a fuse link will protect the conductors and the modules from overcurrent faults. And of course, this will isolate the fault string so the rest of the PV system can continue to generate electricity. So let's say, for example, if we have a short circuit here in this group of panels here, when the current will go from here through this fuse, and the current will go here through this fuse, and the current will go here through this fuse, what will happen exactly is that this fuse will break, okay, it will be burned and break, and it will isolate this part from the rest of the PV system. Okay, so the rest of the system, this string and this one will continue to provide electrical power to the system. Now the last thing I would like to mention is that, again, you don't have to add fuses in the positive and negative terminals. It is enough to add in the positive terminal of the PV panels. Okay, the positive and negative is recommended by Cooper Bus Min company, okay, which provided fuses for and the PV protection devices for a PV system. Thank you for watching this lesson. I would like to invite you to our academy, Khadija Academy Premium membership, which will help you learn more about electrical engineering. In this academy or in the academy membership, you will find that we'll have more than 100 courses in math, electrical engineering basics, power engineering career preparations. For example, we have electrical design, we have courses on electric circuits, power electronics, ETAB, MATLAB, solar energy, wave energy, wind energy, and much more. You will find also in this academy, you will find the different feedbacks from some of our students that joined our courses. You can, for example, join our membership for just a small fee per month, or you can just have a lifetime access in which you will get all of current courses and classes, and you can have them forever. And not only this, but any new courses that will be created, you will be able to watch it for completely free. So what are the classes that I will learn in this membership? You will find different classes in electric circuits, you will find in transformers, magnetic circuits, machines, power electronics, load estimation, lighting design, lightning also design, earthing system, cables, generators, light current systems or low current systems, off-grid design, on-grid design. Very lots of classes and courses in different topics. Okay, and you will find that inside, when you join this membership, you will find this blueprint that will guide you in which classes you will start with when you join this membership. So thank you, and see you in our membership on Khadija Academy.